Hey friends, welcome to Ghosh for AI. My name is Shananda Ghosh, and this is the third video in the 5-part series where we're talking about machine learning algorithms in general, which is very essential to know before jumping into more complicated stuffs like deep learning. In the first two videos, we have talked about the Kernel classifier and the k-means clustering algorithm. If you haven't seen those videos, please check the other videos in the playlist. And now we are going to a bit more complicated algorithm called the support vector machine. Now, the reason I chose this algorithm for a part of this series is because of the role it plays in the history of machine learning. So in around 1985, when Geoff Hinton proposed the backpropagation algorithm for multi-layer neural networks, it was kind of a revolution in the field of machine learning, where neural networks can be implemented for large-scale problems and much more complicated problems. But the thing is, as time progressed, in a matter of say 5 or 6 years, what was seen that this neural network suffered from a problem called vanishing gradients, and because of that, deep networks could not be built. And in that period, around the mid 90s, this support vector machine this was proposed, and it kind of shifted the focus of machine learning research from the neural network to a new paradigm of learning called the support vector machines. Now, this sector of algorithm also deals with something called kernels, which is a nice way to deal with nonlinear spaces where we have to learn nonlinear concepts. I will discuss more about what these nonlinear concepts are as I go on and explain these things. Now, as we know that it all comes down to drawing a straight line. So in the previous clustering video also we saw how we can draw a straight line between two groups of samples to create a separation between them. This is called something called a hyperplane. Now the goal of almost any machine learning algorithm is to find this hyperplane to differentiate between samples. Now this hyperplane, if we consider it as a straight line, it can be written in terms of the equation which is like y equals to mx plus b. That is the equation of a straight line. So here we see a function of x, that is the sample, given some weights w, a bias b, and a kind of conversion function called phi. Now what this phi does is it is like a feature extractor of the raw samples. So the sample is x, and phi of x basically gives me this some features of this sample. Now we generally do not always deal with the raw sample as it is. Most of the time, especially for techniques like support vector machines and the other ones that we have mentioned before, we draw something called the features. We extract features from the samples. So phi x is simply a function that extracts some features from the sample x. Now it is multiplied with some weights that define the angle of this line, and then a bias is added which defines the y-intercept of the line, basically where this line is positioned in the this plot, the area of which is plotted. Now as we know, this is exactly similar to the equation of the format y. This is y equals to m x plus b, or mx plus c, as you write it, as you're more suitable to write it. And anyways, like, so this is the equation of the straight line. This is what we have to find. This is what almost every algorithm tries to find. So if we try to draw a line that separates these two clusters, we can see that. Let us consider this fat line that we have drawn here. Now the nearest point to this fat line belongs to the green cluster, and if we see the same distance on both the sides, we will see that they're a bit far from the blue cluster. So the ideal place for a hyperplane is in the middle of the nearest point from both sides. So if we consider the nearest point from both sides, and if we draw the hyperplane in the middle, this is like the hyperplane that kind of increases the separation between the two clusters. Now the thing is, this is one of the many straight lines that we can draw between these two groups. So if we rotate this straight line in some different direction, we'll get some different set of nearest points, and we'll get a margin whose width is given by this formula, which is mod of fx by this L2 norm of the w vector, the width vector. This formulation of margin is something that is typically the distance of a point from a straight line, and this equation can be found in any of the books on geometry. And these points which like closest to this hyperplane, these are called something called support vectors. Basically these are the support for this vector. We consider the line as a vector, these are the samples that support this vector, so it's called the support vector, and this entire system is therefore called the support vector machine. Now our goal, because we have many options of drawing this line, even intuitively we can say that we should be drawing this line in such a way that this separation between these points, that is the margin, is maximum. So our goal is to maximize this margin. The reason we are doing that is because we want to create the maximum distance between the two different clusters. Now in previous clustering video I have just mentioned a little bit about something called a cluster validity index. Now one of the ways of defining a cluster validity index is basically the intra-cluster distance should be minimum. That means the points of one cluster should be very close and very near to each other, and the inter-cluster distance should be high. That is, points belonging to different cluster should be as far away as possible, and therefore we can say that we can draw this hyperplane in a way such that we have the fattest margin in between them. So we can rewrite this margin equation of fx by L2 norm of w as something like this. So fx is basically w transpose x plus b by w. We can use a multiplier of say kappa in the numerator and denominator now, and we can choose the kappa in such a way that the points which are nearest to the margin, these points, here the fx value becomes 1. So we can use select this kappa in such a way so that fx equals to 1 or minus 1 for the point closest to the line. Then the maximum margin, it is given by 1 by L2 norm of w, because this top portion will become 1. And so say this is the maximum separating hyperplane, and by simply maximizing this condition we can achieve the angle for which this hyperplane gives me the maximum margin. Now this is all well and good, and this all seems quite simple, but the main question is a straight line enough? And so here we are seeing that we are drawing the equation for a straight line, but is a straight line enough? For example, if we have this distribution here that we are showing you, so we have some bunch of red samples which is surrounded by yellow samples all around it in a concentric manner, and of course we cannot draw one single line that separates all these points in an effective way, and it's one straight line, it's not possible. So what we do is we employ something called the kernel trick in the support vector machines. This is one of the largest contributions that support vector machines has brought to the machine learning community, that's called the kernel trick. And with this kernel trick there have been a lot of different ways the research has progressed, especially there are different kind of kernels that has been made, like linear kernel, polynomial kernel, RBF kernels. There are also kernels for different kinds of data, like for periodic data, or say for even for graphs there are something called graph kernels. And this kernel based research is also something that's very kind of like it's very appealing to researchers. So if you're looking for topics of research, if you're good in mathematics, if you're good in this kind of mathematical solutions of machine learning problems, if these things appeal to you, you can also look for you can also try to find a new kernel for new problems basically. So that's a point of research that you can work in. Anyways, coming back to the point, so is the straight line enough? And of course the straight line is not enough to separate this kind of clusters. So what the kernel trick does is so this is a lower dimensional space. Okay, so this is the two-dimensional space that we are showing you. So the kernel function, it maps these samples into a higher dimensional space. So we can consider this three-dimensional volume. It looks like something like a three-dimensional glass. That will say the glass of water that we drink looks like a glass or something with a round edge or a rounded bottom edge. The kernel function basically maps these points from a lower dimensional space to higher dimensional space. And say the kernel function is kappa in that case. Okay, we should not confuse this kappa with the one used here during explaining this equation of maximum margin. Please do not confuse the two kappas. They are completely different. They have no relation in between them. So say the kappa is a kernel function that basically maps this point from the lower dimension to the higher dimensional space. So as we said, the kernel function can be a point of research. There are many kind of kernel functions present: linear, polynomial, RBF, periodic, Gaussian, and many more things. So here you can kind of assume that this is something of a polynomial in nature, which plots these points in a curved surface. And the beauty of this thing is that now we can use a straight hyperplane. Like so in case of a two-dimensional space, we use a single straight line. In case of a three-dimensional space, we use a plane. For higher dimensional space, we use something called a hyperplane. So but hyperplane is a generic term. So in this higher dimensional space, we can see that the use of this hyperplane is like with the straight hyperplane, we can separate these two clusters in a very nice way. And what we are doing is basically we have this transformation of the input space with the kappa function, and we are drawing the hyperplane on this transformed sample space, that is the kappa x. We are drawing the hyperplane on this transformed sample space. This is the equation for a hyperplane, but instead of working on x, it's working on kappa of x. And with this okay, now so that we can separate these 2 points, but that's not enough. We also have to find this separation in our actual space. If we don't find it, it's of no use. If we find the separation in a different space, we have to find the separation in this space we are working with. And for that, we simply use another function that kinds of inverts the effect of the kernel, and we map back this intersecting plane to the original dimension, and we can get this nice elliptical hyperplane kind of thing, or elliptical separation kind of thing between the two clusters. And this is something called the kernel trick. And now, okay, so now the question would be, okay, so for this kind of sample distribution, we can map them onto the back of this inverted rounded bottom glass kind of thing. But what if this distribution is something else? What if this distribution looks like something different? That's the thing is, then we have to map it to a surface which looks different. So the choice of the kernel function is important while keeping in mind what kind of distribution we are dealing with. So depending on the kind of distribution we're dealing with, or the kind of nonlinear hyperplane that we need, we can choose the kernel function accordingly. So say if our data is periodic in nature, we use a kernel function that is a periodic kernel. If our sample distribution is Gaussian in nature, we use a Gaussian kernel, and so on. So with this, we can say that, okay, this is the end of the support vector machine section. And here you have learned how we can use this kernel trick to map samples from one lower dimensional to higher dimensional, and we can draw this hyperplane in that dimension and then map it back. We have also learned how we can use the support vector machines to find the maximum separating hyperplane between these two sets of samples. And I will tell you that support vector machine is still today one of the state-of-the-art machine learning techniques, and it goes quite toe to toe with many modern techniques like neural networks and even some of the deep neural network algorithms. And so, and it's very important for new researchers, as I've said before. And now we'll be looking to some of the references that we have. Again, there is this Weka and Weka 3, which has this libSVM support. libSVM is It's one of the most commonly used library for support vector machines, libsvm, and Weka 3 has a support for the libsvm package which runs in the backend. Otherwise, you can use the support vector machines for binary classification in MATLAB, or you can use support vector machines in the scikit-learn technique, which works with Python language. We have some blogs which explains the mathematics behind support vector machines. The mathematics behind support vector machines is a bit complicated, but it's not something that you can't understand, so you just have to go through. I'm not going through the in details mathematics in details right now. It's kind of beyond the scope of what this tutorial is supposed to mean. And we should also point you to two specific papers. One is the support vector machines, another is this is the measuring the VC dimension of a learning machine. This VC dimension is something which is very much important when it comes to support vector machines. Please look into those papers and try to understand the maths. Maybe I will make future videos in which I try to explain the maths, but I would be honest that I'm not very good at maths myself. So I might not be able to explain them in the best possible manner, but there are many other sources in where you can find these explanations. I can also, one of them is not listed here. There was one video, I don't remember the name of the professor, but I think he was from Caltech. Let me just search for you. Support vector machine. So there are many resources that you can see in support vector machine. Okay, so this lecture, this is one of the best lecture that I found on support. It's from Caltech. I would please suggest you to follow this video. He explains the mathematics behind how it works, and this is a good explanation. So with all that, I would bid you farewell for now, and I'll be back with one more algorithm in the next video. Thank you and have a good day, and thank you for watching. Okay, so I'll be giving a link to the presentation that I'm using in the description below. If you liked the video, give me a like, or if you didn't like, give me a thumbs down and tell me how I can improve this video. And also tell me about what kind of things you expect from me, or if you have any questions, ask me in the comments below. I will try my best to answer them to the best of my knowledge. And subscribe for getting more updates in the future, and don't forget to click the bell icon for notifications. See you and have a very good day, and thank you for watching.